Good afternoon, everyone. Welcome to the 8th session on chemical engineering thermodynamics problem solving session. Today, the topic is on thermodynamics are not only function of T and P, but now they are function of T, P, and Xi or Ni. Okay, and if we differentiate it like total differential, then it is obtained as dou Ng by dou P, T comma N. It means this is at constant temperature and number of moles, all the number of moles into dP, and similarly for temperature, and this is for moles. Okay, this will be sigma of, like, I have two species assume, then by dou N1 into dN1 plus by dou N2 into dN2. So summation of things will be there. So here, what is there? Dou Ng by dou Ni at constant pressure and temperature and other moles of other species, other components, then it will be mu I. This is named as chemical potential. Okay. So here we can see on comparison with this and this here. So we already know this NS is this one. So we already know that dou of Ng with respect to dou T at constant P equal to minus Ns, right? And here, sorry, no T, and this is P. Okay, so we know that this term is minus Ns. And similarly, this NV is given for this. So NV dP minus NS dt plus this is mu I, right? So sigma of mu I into dni. So this is there. So we have these relations. Well, this is equation 1. One more equation is, I'm assuming Nj also here. And everything, okay, and everything. And also dou Ng by dou P at constant P and N is equal to NV. And this is equation 2. So we have got relation for S and V. And now we have relation for G also. And H we can get from G plus TS. Right? So like this is DS. Sorry. Yeah, okay. When you have a relation for G already, so you get what is S also, what is V, and also H, which is defined as G plus PS. So the if we have a relation for G, then we'll have the complete property information. Okay. So that's how. So here, yeah. Right. So how I said is this is liquid phase alpha, not liquid only, alpha and beta phase. Okay. So one more thing I want to say here, if it is a one-phase system, or two-phase system, and it is a closed, then again the initial equations which we have defined, dg d of ng is equal to this one, minus ns dt plus nvdp. So this is followed already. And also this equation dng is equal to ns minus ns dt plus nvdp plus mu I dna is also followed. So that and this both are followed. It implies that the sigma of mu I dni is 0 for a closed system. So this is, I'm talking for the whole system. If you consider this is followed, and even if it's a single phase, that is followed. That's why we have removed that term, and only this term is expressed for the single phase system, right? And when we come to individual phases, the same relation can be expressed as dng for alpha phase, okay, and also for beta phase. So now for the whole system, it can be expressed as summation of these, okay, right? Because these are like extensive properties which are based on the mass of the system, like whatever is there. So energy properties are like summation is understandable, right? So that's why we sum up the nm of alpha and beta. Here m is extensive property and molar property. Okay, molar means per mole. So that's why we multiply it with n. So when we check out this, so similarly for the alpha and beta, if we sum up, this is NB, right? That's why we get the summation of these things. And as we know, for the whole system, this summation is 0. So summation of these should be 0 here at for the whole system. And also when this is equilibrium, right, at the equilibrium, this becomes 0. So this is given as d of ng, right? That's why this is 0. And we know one more thing is that because the both phases exchange materials, so whatever number of moles are lost by this phase is equal to whatever number of moles are gained by this phase, this one. Okay, of the each species also, okay, different components also. It's not like total number of moles are conserved or something, okay, in this. I'm not saying that in this phase completely only 50 moles are there, okay. To attain equilibrium, they are exchanging things. So for a given temperature and pressure, generally, if I'm talking about like water and water vapor, okay, liquid water and vapor, then at each equilibrium, there will be some humidity in the air, right? So similar to that, there will be some water in the air and completely water in the liquid mixture. There can be some air inside the liquid also. So that's why we have x1, x2 and y1, y2. Okay. Now, if I change some temperature or pressure, okay, then the new equilibrium point has to be attained. So then what happens? Just a small exchange of mass happens here to attain the new equilibrium. So here, I'm only talking about two species. Okay, so if 50 moles of phase of liquid phase is there, and out of that for example, 5 moles of air and 45 moles of water is there. And in this, for example, 40 moles of air and 10 moles of water is there. Okay, so out of 5 moles, maybe this time 2 moles will go. So of course, this will gain 2 moles of air, 40 plus 2. And out of 10, maybe 3 moles of water will come down, so plus 3, right? So how many moles of each phase are there now? Minus 2. 3 plus 48. 51. And here 42 plus 7. So 49. Overall moles of the system are conserved, but it's not necessary that number of moles in each phase has to be conserved. But the transfer of specific component or species in a phase, they are exchanging the same material. So that's why this is DNI alpha. The is same as like gain and lose, or the ulta also. That's why minus sign is used here. So considering that in the above equation, which is this one, so considering that, we get sigma of mu I alpha minus mu I beta is into DNA alpha is 0. Assuming that there exists some finite transfer, so this is not equal to 0. So that's why this should be equal to 0. So that's why at equilibrium, mu I alpha is equal to mu I beta, which is like generally you say mechanical equilibrium. Okay, you say force 1 is equal to force 2. Right. Not pressures. Please note that is force balance we do. And heat equilibrium, thermal equilibrium, if we say, we do T1 equals to T2. Similarly, when it comes to chemical equilibrium, it is mu1 is equal to mu2. Okay, it's not concentrations equal, its chemical equilibrium is potentials are equal. Okay. Now, and how is chemical potential defined as dou Ng by dou Ni? At P, T, Nz. Mu1 alpha, mu1 beta, okay, or else mu I1. I'm just correcting the above statement, that's all. Okay, so P and T and Nj. So that's what we mean here is at constant pressure and temperature, this mu is defined, right? So like at an equilibrium, we are defining it. So that's why the statement is given as thus multiple phases at the same temperature and pressure are in equilibrium when the chemical potential of each species is the same in all phases. So this is what we have learned till now. What is the fundamental property relation for an open system? How is it changed? And then what is the definition of chemical potential? And how is a chemical equilibrium defined? Now, as I said earlier, the total properties are obtained when we have models for the G and this mu I also. Dou Ng by dou Ni. So when we have G, then we have relation for mu I also at constant pressure and temperature, right? Mix of mixtures. The course instructor is Professor Shashidhar Guma from IIT Tirupati, and I am Namrata Kulkarni, PMR scholar from IIT Madras. So, till now we have learned initially what are the fundamental property relations here. These fundamental property relations for a closed system. And in the last week, we have discussed for an open system, not only with respect to pressure, this any molar property changes with the composition of the mixture also. So here T, P and Xi or Yi, the composition, all these three play an important role in determining any molar property. So similarly, the derivations for the Gibbs energy, enthalpy, and also this is entropy and volume. So we have got expressions for all the molar properties. And later we discussed what are the partial properties. So there are three distinct types of properties we can discuss as shown here. One is the, for example, I have a pure species 1, okay? And I have pure species 2, where it is cross. So I have a mixture of these two species. Okay, the property in this is M. Then property of 1 is M1 bar, and this has a property of M2 bar. Whereas here it is M1 and M2. So this is the one we have discussed earlier and how they can be related. So for the overall property of a mixture, it is summation of Xi into Mi bar. It is not Xi into Mi, but Mi bar is defined. So how this Mi bar is derived and all, we should be discussing and all. Yeah. So coming to the like generally, we have discussed earlier also that for a pure species, for a gas or for liquid, for a pure species, there are different kind of models like ideal gas, Redlish Kwong, and so Redlish Kwong, Peng Robinson, sorry, yeah. All these we have discussed. So similarly, for the mixtures also, we have different kind of equation, equation of state. Okay. So like that, we'll be discussing different things. Generally, here we are having molar property of mixture M. Mi bar is partial molar property of component I in the mixture. And this is property of pure component type at the same T and P. So ideal gas state mixture. So now we have gases, liquids. So like generally we know ideal gas for law also, right? PV is equal to RT. Similarly, we have ideal solution also, okay? It's ideal gas mixture. And this also follows PV is equal to RT and ideal solution is also there similarly. Okay, we'll be discussing about that in later sessions. Now today we are going to discuss about the ideal gas mixture model. So this is mostly valid in the limit of zero pressure And this is can be considered for so many systems because it has a molecular basis. It defines system on like it assumes zero volume for the molecules, and it assumes no interaction among the molecules. That are the only assumptions here. So it is developed based on the molecular system, and it is very analytically simple. Okay, so here we say for an ideal gas mixture, the V is RT by P. So the mixture has temperature and pressure T and P. Okay, and for each thing, we have VI, IG bar. Okay, this is MI bar. And it is IG, ideal gas model, right? So that's why we are putting ideal gas. So later we will be discussing other models. That's why we have a subscript IG here as a, like we will be using this model as a reference and other models for usage. And we use a property like M residual is equal to M minus M IG. Okay, it means like how much is it deviating from the ideal gas mixture model that is given by residual model. Okay, we'll be defining this later. So that's why we are using an superscript here. Okay, so now VIIG bar is defined as dou NVIG by dou Ni. Okay, on differentiating this with respect to Ni, then we will be getting same RT by P, right? So that's why VIIG bar is equal to VIIG here. Okay, it is equal to the pure I. And this is I in mixture. Okay. So last week we have learned that M is equal to total molar property is equal to summation of this molar fraction into Mi bar. I have shown this here, right? Xi bar. This one is used here also, but since it's a gas mixture, we have Yi. This is also molar fraction. So that gives us V of Ig at T and P. This is for the mixture is equal to, this is I in mixture. Okay, Yi into this. And this is equal to pure thing. So pure I. Right? So here we can define delta V mixture in ideal gas model equals to 0. Okay. Right. So here, using this molar fraction, we define a partial pressure, which is equal to RT by VIG into Yi. Okay, this YIP. And this sigma Yi equals to 1. And also, one has to know that here, as I said, for example, this is one molecule, blue color, and another one, this red cross. This VIIG bar is the so this species has a pressure of PI, okay, which is equals to YIP. So VIIG bar is similar to equals to VIIG at PI, okay. So this VIIG bar is defined at the temperature T and pressure T, which is the overall pressure. But it is taken as it is equal to the molar property of the pure species at Pi in the ideal gas model, right? So this is understood first thing, and this is also understood. Right? So we have done this for the volume here. Later, for the other things, we know that as the pressure is very going to tends to 0, and in the ideal gas mixture model, the enthalpy and entropy are independent of pressure. So that's why we know this MIIG bar at T comma P equals to at T comma Pi, right? So we can almost say MIIG bar equals to MIIG at T and P for H and S. So that's why this is defined at T and P only, not T and Pi, because anything is same for enthalpy and entropy. Okay. So now we have this ds ds is equal to Cp dt minus dou v by dou t into dp at constant p, right? So at a constant temperature, if I define this is 0, so ds I at Ig is equal to minus R d ln Okay. So that's why SIIG at T and P minus SIIG at T and PI is equal to minus RD. Sorry, yeah, if it is integrated, minus R and then P by PN, which is R ln YI. So I have SI IG bar equals to SIIG at T comma P I. So PI, right? So here what is PI? So this is equal to SIIG at T comma P minus R ln yi. So this is here inserted here. Okay, so this is how we get this equation. The next equation is GIIG bar. So we know GIIG bar equals to HIIG bar minus TSIIG bar. By inserting things here, HIIG minus TSIIG minus R ln yi. Okay, this is all are defined at T comma P. So that's how I get this equation. So later we have discussed this right already. It's a summation of things. For the volume also we have done. So resultant we get H of, this is the property of mixture and this is the property of purine. So we don't know what is Mi bar in a mixture. Okay. So that we are expressing in terms of Mi, which is the pure thing. So we know the values of pure species, and when it is in a mixture, how is it, what will be the overall property of the mixture that we want to know. So what all parameters it can depend on is, like here we see this enthalpy is dependent on the mole fraction. Okay, and this entropy is dependent on mole fraction only. Whereas coming to this, the Gibbs energy depends on temperature and also mole fraction. Okay, fine. Now, coming to that, the Gibbs energy thing can be described in a different way also, because we know dG equals to VdP minus SdT. At constant temperature, GT is equal to 0. So, DGIIG for the pure species, I can say, is equal to VIIG dP equals to RT by P dP equal to RT ln P. On integration, I will get GIIG equals to some integration constant, which is a function of temperature. Okay, so this was excluded, right? Generally, G is a function of T and P here, but we have excluded this property, this thing. So at constant T, so this should be used here, right? So that constant is dependent on temperature and plus RT ln P. This was D ln P. Fine. So this is derived here. Earlier also it was the similar, but here it was summation of like it's only dependent on this temperature and yi. But here I'm writing it in terms of temperature, pressure, and yi. This P, if it is going into a mixture, the same thing can be described as YIP. Okay, RT ln YIP. This P will become PI, right? Inside the mixture. So that's how I'm defining this GIIG bar. Now, this is I in mixture. This is pure I. This is for the mixture. Gij equals to sigma yi into Gi bar, right? So from that we get yi tau it plus rt sigma yi ln yip. So this is that. So now what we want to define is if some other model I'm using by removing the assumptions of no volume, no interaction, these kind of things, what will be my properties? The Gibbs or enthalpy or entropy or volume. Okay, like I explained in previous sessions, if volume, for example, I have added two liquids of okay, two gases only. I don't want to deviate. So two gases which has 1 meter cube volume, but upon adding, if they are if the molecules are attracting each other, they have van der Waals forces and something like that, then the volume of the whole system will be decreased. It won't be 2. It will be somewhat 1.7, 1.8 like that, meter cube. So that is accounted in different models. Okay, ideal gas mixture won't account that thing. That's why we have delta V mixture is 0 in the ideal gas, right? So, okay, I want to make a note of those things. Hmm. I want to erase it here. Okay. So delta V mixture in Ig is equal to 0. Delta H mixture in Ig equals to 0. But coming to delta S mixture in Ig equals to Si, sorry, Sig minus sigma Yi Sig. This is defined like this, okay? Equals to R sigma Yi ln Yi. And the next one is delta G mixture Ig equals to RT sigma Yi ln Yi. Okay, so please make note of this. Now coming to the analogous thing, that what I said, model deviating um, model which is able to describe deviating from ideality. Okay, so in that the analogously the G to I this gamma I plus RT ln P is there now. This will be ln Fi now here at constant temperature, right? And this is for the pure species. And this is I in mixture. Okay. And again, you know how this M is equal to sigma xi Ci bad. This you know, right? Xi or Mi for gases. Okay. Right? So this is the fugacity we say, which has a units of pressure here, similar to this equation for an ideal gas. And in the mixture, it is represented by phi hat. Okay. This is the fugacity of species I in the mixture, which is same as YIP in an ideal gas mixture, like this. Now, I define residual property. This residual property is defined for gases, whereas excess property is defined for liquid solutions. Okay, so GI minus GIIG, GIR is defined as RT ln FIP. FI by P, okay? And here, this is phi. So this minus this we are doing. And that's how we are getting Fi by P. So that's why we have fugacity coefficient. So it is pressure by pressure, right? This has pressure units both. So this is dimension less number. And similarly for the mixture thing, how much is it deviating from an ideal mixture? The residual property is defined and we have phi I hat there. Okay, so this is all what has been discussed by Gumasa in the week 8 classes. Now we'll just pick up few questions and go through them. Okay. For an ideal gas, the entropy change of mixing depends on. So as I said, delta entropy. Okay. Entropy for mixture ideal gas equals to R sigma Yi ln Yi. So it only depends on the mole fraction, the composition of the mixture. Now, the Gibbs energy change of mixing depends on what? Delta G mixture Ig equals to RT sigma Yi ln Yi, right? So it depends on the temperature and composition of the mixture. Now, the binary mixture is prepared by mixing 100 moles of each of two ideal gases. So 100 moles of each. So N1 is equal to 100, N2 is equal to 100. So these are gases, right? So Y1 is equal to 0.5 and Y2 equals to 0.5. Okay, the entropy change. The entropy change of mixing, the delta S mix Ig equals to R into sigma of, right? So 0.5 ln 0.5 Yi ln Yi, right? Plus 0.5 ln 0.5. So this is equal to his here, this here. R into ln 0.5, 0.5 plus 0.5, 1, right? A terminal mixture is prepared by mixing 100 moles of each. The Gibbs change energy of this will be delta G mixture Ig equals to RT sigma Yi ln Yi. So it will be RT, the sigma Yi 0.5, right? As we seen in the last question. So this will be ln 0.5. And notice, this should be in Kelvin. And this is R8.31. Okay, fine. Now, 0.75 meter cube of CO2 and 0.25 meter cube of N2, each at 1 bar and 25 degrees, are blended to form a gas mixture at the same condition. If CO2 and N2 are having and like ideal gases at this condition, the change in entropy is equal to the delta H mixture for ideal gases equals to 0, right? We have discussed earlier. So that's why this is 0. The fugacity of species I in an ideal gas mixture equals to. So we have discussed Fi is for pure species. And Fi hat is for I in mixture. Right? So here we are been asked the fugacity of species I in an ideal gas mixture is this Fi hat, and this is equal to Yip in ideal, and this is P in ideal. So it's partial pressure. It's equal to Pi, right? That's fugacity coefficient of species I in a solution. So one thing. So what phi I told was for the gases. But for solution also we express the same. So for gases, how do we define Fi by P, right? Or in a mixture, Fi hat by Yip. Similarly, for liquids also we define the same. So it has no dimension, right? Now, as pressure approaches 0, the ratio of fugacity to pressure for a gas approaches. So, the first thing is you might be thinking F by P, so pressure tends to 0. But this doesn't tends to infinity because this also F also becomes equals to P here. When pressure tends to 0, it behaves as an ideal gas system, right? That's why it will be going to unity. So this was a very simple thing till now. So this week we have just took very simple questions out of this thing. So later we will be discussing the next week's sessions. Thank you for today.